Now this next thing is I will swap that nth song with the x minus one song, right? Which is 1 billion minus one song, right? So the played song is now at the last of my array. Now I will reduce my length of the array from x to x minus one, right? Since now my array contains 999,999,999 songs, right? So with this, I've moved my played song to the last. Now what I'm gonna do is I will again go to the steps two. What I will do is I will again find the random. I will generate a random number between 0 and x minus 1. Now I've already reduced x to x minus 1, so here it becomes x minus 2, right? So I will generate a pseudo number between 0 to x minus 2. Right now, let's suppose it's again nth, and I will play the nth song and will swap it. So basically, in this scenario, we don't use any time complexity. It's big O one, right? We don't use any extra space complexity because we are not storing any variable anywhere, any song anywhere, right? All we have to do is just swapping them. So by doing this, we have created a function using basic arrays, which solves a real world problem for us. Right. So arrays are pretty useful when it comes to industry these days. Okay. Now let's just talk about let's just discuss what we have discussed till now. What are arrays? Arrays is a continuous area of memory. If it is not continuous, but all we cannot do a simple arithmetic to read and write operations, right? Or how do we define an array? We allocate a specific chunk of memory, then we divide that chunk into different equal uh, small chunk of memory, and then we assign index to it, right? To perform read and write operation in constant time, the element needs to be of fixed size. So basically, I can't create an array which contains list, which contains string as well as float as well as int. It needs to be a same data type. The last is to read for read and write operation with constant time on a specific instance. It takes constant time. Add and remove at the end takes constant time, whereas in the middle or in the beginning it takes linear time. That is, it depends upon the length of the array. Okay, so we have discussed what array is. Now let's just jump into divide and conquer. Okay, so I guess everybody have heard in history that divide and conquer is a very pretty old term. It's pretty old term. It was used in wars, and at that time, what they used to do is to split that army into into smaller chunk of armies, or what they do is they just try to divide the opponent's army into smaller chunks so that they can win over smaller chunks of army rather than defeating the whole army at once, right? So a divide and conquer algorithm uses this approach to solve problems, right? What we do in divide and conquer is we take a problem, we divide that problem into smaller chunks of problems. It needs to be the similar problem. We can't go and create a different problem out of this problem. So it needs to be the similar problem, but on a smaller set of data or a smaller set of smaller set of data or smaller set of something else, right? So it needs to be of the same time. We can't create different set of problems within a problem, right? So if you see, the problem needs to be it needs to be non-overlapping, and it needs to be of the same problem. So basically, if you see, if I have a problem in the blue, what I will do is I will divide this problem into small problems. Since I have talked about, I put a very like a huge emphasis on it needs to be the same problem. So if you see here, there is a rectangle box, there is a triangle, there are three triangles. So if I talk about, these problems have changed now. Whereas the problem was a square or a four sided shape, now it have changed to three-sided in the division, right? It is not possible. We can't use divide and conquer to solve these sort of problems. In the second, you can see it needs to be non-overlapping, as in we can't take we can't have a union of problems. We all we have to do is to make them non-overlapping. Only then we will be able to solve the problem. So how do we solve divide and conquer, right? What we do is we take a problem, we divide into smaller chunks of problem. In this, you can see the blue box is now divided into four smaller chunks of problems, subproblems. Then we solve each of these small subproblems separately, and then we combine all the solution of whole these four subproblems to come up with the uh, answer of the bigger problem, to solve the bigger problem, right? Yeah. So here a very like a very frequent question is basically how do we small these smaller chunks, right? If you see, if I talk about just the yellow box, right? I can just apply divide and conquer on this again. What I can do is I can subdivide the yellow box into smaller chunk until I reach to a situation where solving a problem for me is not a big task, right? We will just talk about how this happens. But basically is we just keep on subdividing the problem in such a way that solving a problem becomes quite simple for me, right? So let's talk about linear search, right? How linear search works. So we've talked about array. So linear search is basically helps us to find an element within an array. We talked about we can reach to an index in constant time, but finding the value takes time, right? We don't know where the value is stored, like where the 10 is stored, where the 15 is stored. We don't know the index. So basically, with linear search, we are trying to find the index where X value is present, right? So what we do here is we traverse the array from start to the beginning, and what we do is we check the value with the target value. If it is there, we return the index of that particular element, right? So it's pretty simple. What we do is at index I, so basically what we do is we have array A with n elements. All we have to do is find k. If a of I is equals to k, we return I. Else we say that we not found, k cannot be found. Okay. So if I talk about the recursive algorithms, a recursive algorithm here, right? What it do is it will keep on dividing the problem into a sub problem until I will be able to solve that problem, right? What we discussed with divide and conquer. So we will loop till if high is less than low, as in um, so for example, to start this algorithm, what I will do is I will start with a low is equals to 0, high equals to n, and where n is the length of the array. Key is the target value, which I need to find. If high is less than low, I will say not found. If a of low equals to key, I will say low. That is the index of that element where target is present. If not, what I will do is I will recursively call the same function a low plus one, high, and key. So if you see, we are not subdividing. What we are doing is we are just dividing the problem by a factor, not by a factor, but we are just reducing one element for search for the next sub problem. So we are not just dividing it, we are just extracting one element at a time and just we're checking the value for it, right? So that's why some people say that divide and conquer is linear search is not a divide and conquer algorithm, right? By divide and conquer, people say that divide and conquer needs to be where the problem is divided into some percentage of the problem, as in 50%, 60%, 25%, something like that. Wherein in this scenario, what we are doing is we are just reducing the problem by from n to n minus one, right? So it's not exactly divide and conquer. It can be called as subtract and conquer because we are just reducing the problem by one. Okay. Okay. So let's just jump to binary search. Okay, so binary search is an optimized search algorithm. If you, we will talk about the time complexity later, but linear search takes big O and as a time complexity to find a particular element. So it needs to be optimized. We can't have a search algorithm which is dependent on the length of the array. So what we do here is we basically uh, use another set of algorithm. The constraint for using this algorithm is basically it needs to be on sorted array or sorted with repeated or with or without repeated elements. So if the array is not sorted, we can't use binary search. So here the input is basically again a sorted array from a 0 to n, and the target value where is k, which we need to find within the array. Now the output is basically index I if ai is equals to k, or the greatest index I where ai is less than k. So basically, if let's suppose if the maximum element that is present in the array is 20 and I need to search 25, right? Since 25 is not present, what I will do is I will return the index of I, that is index of 20. And the other is the output will be result will be low minus 1, where k is less than a minus low. So for example, let's suppose the first index of the sorted array, the first element of the sorted array is 10, and we have to find 6. Since it's not found, but binary search, what it returns is it returns minus 1, as in it is not found, right? Okay, let's just see how binary search, what is binary search, like what we discussed right now, right? So this is the array we have, indexes from 1 to 7, right? If I have to find 2, since it is not there, based on our algorithm, if k is less than a low is a of 0, a of 1, which is 3 in our scenario. Since k is less than that, search of 2 will become 0, right? Search of 3 will become 1, search of 4 will become 1, right? Since in this scenario, if you see in this, so the greatest index I, where ai is less than k. So what we have to do is we have to find the greatest index which is less than the value of the target. Since the target is 4 here, we don't have 4 in the array. What we will return is we will return the index of the value which is lower, which is just lower than 4, which is 3 here. So we will return 1. Search of 20, it's there at 4. Now there are two indexes with value 20. So based on different ways, this 20 can be either 4 or can be 5. And search of 60 will be 7, whereas search of 90 will be 7, as well as we have to return the the index of the value which is just lower than the search element, which is 90 here. Okay. So now just let's just look into binary search from the recursive manner. How we solve binary search, right? We have talked about linear search. It's simple traversal, but binary search. So basically, how what we do is we split the problem into two small chunks and then recursively solve it. So what we will do is we will start with the middle term. We'll just reach out to the middle term of the array. We will compare the value, the target value, with the middle value. If it is lower, then we will go on the left side of the array. If it is higher, we will go on the right side of the array. Right? This is how it works. Let me just give you an example how it works. So now we have an array from 0 to 16 elements. We will start with the middle array, that is 8. Right? Now we have to find is 7. The element that we have find is 7. Now 7 is lower than 14. Since it is lower than 14 and it's a sorted array, we know that 7 will be present on the left side of the array, not on the right side, right? It's lower than that. So what we will do is we have subdivided the array from 0 to 16, from 0 to 16 to 0 to 8. Now again, we will recursively use the same algorithm to find the middle first. Now the middle becomes index 3, right? Now with index 3, the value is 6. Now 7 is greater than 6. Now since 7 is greater than 6, we will go to the right side of the array. Now from 0 to 8, the problem has subdivided from 0 to 8 to 4 to 8. Now we have to search for 7 from within index 4 to 8. 4 to 7, sorry, 4 to 7. Okay, now the middle term will be 5. We see that 7 is less than 5. Based on since it is a sorted array, we will go to the left side of the array, which is from 4. Now the array is just 4, so we will check whether 4 the value of element at 4th index is equal to the target value or not. It is equal to the target value, and we return 4 as the index of the searched element. Now let me just again talk you through what we have done here is we will first find the middle of the array. Middle is basically floor of low plus high minus low by 2. If the target value is equals to array of mid, then we will return the mid as the index of the searched element. If not, then what we will do, if key is less than a of mid, we will recursively call the function binary search with a low mid minus 1. Now you see what we have done here is we have reduced the problem from low to high, as in 0 to n, to low to mid minus 1. Right? We have subdivided the problem into just exactly half, 50%. Right? if key is greater than a of mid, what we will do is we will just increase the value of mid by 1, and we will search the element within mid plus 1 to high. Yeah. Now let's just talk about the complexity of these algorithms. What we have discussed here is these are the recursive algorithms. So to find the complexity of recursive algorithms, we denote a recurrence relation. For recurrence relation is T of n, where T of n shows the worst time complexity of the problem. T is the worst time complexity, n is the size of the problem, right? The worst case scenario in linear search is basically we don't find the element itself. So what we have to do is we have to traverse the whole problem. We have to traverse the whole array, and then we will see whether the element is present there or not, right? So at every step, what we are doing is we are just checking the value of the n minus 1th array with a constant time of with a constant check which takes constant time of c, like a check which takes a constant time of c, right? Here c is the constant amount of work that is being done, right? So if I try to split the problem, it is basically first I will check n minus 1, n minus 2 up to 0, right? So since I have to traverse the whole array itself, the complexity of this algorithm is dependent upon upon the length of the array. That's why it becomes big O n. Sorry, it becomes big O n. The complexity of the algorithm becomes big O n, right? About what about binary search? Now in binary search, the beauty of the binary search is divides the problem into exactly into 50%, right? So how it is done is we check 50% one time and 50% at other time. So here again, T of n is the recurrence relation that is being used, right? But here, since the problem is subdivided into 50 into half, now T of n becomes equals to T of n minus 2 by plus C, where C is a constant amount of work that is being done, right? So here what happens is it's n by 2, n by 4, and up to 210, right? So the complexity of this becomes big O log n, log of n, right? So the complexity of this is log of n. Okay, cool. So let's just talk about a practical example of binary search, right? Why binary search is important, how it is being used. We talked about a very important property of binary search, that it works only on the sorted array, right? Now just take a bit complex problem. Now let's suppose you are given with a rotated sorted array. Now the array is sorted, but it is rotated by a shift which you don't know. So basically now your array becomes 4, 5, 6, 7, 7, 8, 9, 10, 1, 2, 3. So basically if you see, the array is rotated by a shift of 3. Initially, the array was 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 10. Now we have shifted by 3. So now we have to write a function to calculate this, to find the element in this array. I guess we are already out of time. So let me just jump into the solution. So basically, the easiest way or the brute force way is to apply the linear search here. With the linear search, what we can do is we can just start looking at, we can just traversing the array from index 0 to index n. And whenever we find the element, we will just return the value, right? Which is the complexity will become big O n. Now, how can we optimize it using binary search, right? Since we know it's a sorted array, but it's a rotated sorted array. Can we change the algorithm a bit to find the element x, right? So what we can do here is we can start with left equals to 0, right equals to n, right? We will again find the middle of the element. Mid equals to length of n by 2, right? Again, we will apply a floor here if the array is the elements in the array is odd, right? Now the comparison bit becomes a bit complex. So what we'll do is we will check whether a of left is less than a of mid or not. So if we are splitting the array, if we're splitting the array by 50, we are sure that at least one of the array is sorted. Either the left will be sorted or the right will be sorted. There will never be a scenario where both of these arrays will not be sorted, right? A to mid or mid plus 1 to n. So what we'll do is we'll find first which of this array is sorted. It's the left side of the array or the right side of the array, right? So let's suppose our A of left is less than A of mid, right? It means that our left side of the array is sorted. It is sorted. So what we'll do is we will check the target value with the num of L low. So if the target value is greater than the array at lowest element, which is 0 for first instance, um, and target is less than number of the array at mid, right? If it is there, then what we'll do is we will find the target value in 0 to mid, as in we have divided the the problem to 50% exactly. If it is not there, what we'll do is we will find the target variable in the right side of the array. We will just change our array from mid to right. Right. Now let's suppose our sorted array is on the right side of the array, as in right side of the mid. So here the target, if the target is less than a number, like the last element of the array, or and the target is greater than the mid, right? Then we will search in the middle part, mid to right. If not, then we will search for the left side of the array. We will just do it recursively. So we'll go to step 1 again to find the element. Again, just let's just talk about the summary. What we have discussed. We have to break the problem in such a way it has to be non-overlapping, right? We will recursively solve these problems and then combine the problems all together to come up with the final solution.